Hello, class. This is a continuation of the last lecture we had, of course, on biaxial stress, and I just wanted to start off with sort of getting this out of the way because this would just be natural extension of what we were just talking about. We were looking at biaxial stress and how that worked out, and what I wanted to look at was triaxial stress, because triaxial stress would be like if I had some type of, and there's a whole variety of ways that we could do this, is where I had a force in this direction, a force in this direction, right, and a force being applied in this direction. Now I'm drawing them all as tensile forces, right? But they could be, some of these could be tensile, and I'm going to derive the equations as if they're all positive tensile forces. So if I'm pulling this out on here, what would happen? Wouldn't the thing just expand in all three directions? But there would be competing forces that are going on. And so when we looked at the strain in the x direction for triaxial stress, that would be the stress in the x direction divided by E, right? Minus Poisson's ratio times the stress in the y direction divided by E. Just a second, I just realized I forgot to turn my timer on. So, yep, good thing I just didn't tell you my phone combination, but I do have it in my head. There you go. Times Poisson's coefficient in the z direction, that's a z, divided by Young's modulus. And if I wanted to simplify that, what I could say is I have 1 over E times sigma sub x minus Poisson's ratio times sigma sub y minus Poisson's ratio times sigma sub z, right? And I could take Poisson's ratio out of there, if I wanted to too, and it would just be, anyway, you get the idea, because this is going to be in the, what did I call this before? I think I called this the x direction. So this would be sigma sub x, sigma sub y, sigma sub z in those three directions. And so that's what my equation would come out to be. And you can see, now I'm just going to box that in because that's, more or less simplified. The same thing would be true for each of the other ones. So sigma sub y is just going to be 1 over E, and the only difference is that it's going to start off with sigma sub y minus Poisson's ratio times sigma sub x minus Poisson's ratio times sigma sub z. Right, so that would be the strain in the y direction for triaxial stress. And then the strain in the z direction, of course, is just going to be 1 over E times the strain in the z direction minus, oh, where is that pen? Almost made it through, minus Poisson's ratio times the stress in the x direction minus Poisson's ratio times the stress in the y direction, right? So those are our three equations for strain for triaxial stress. And that's what I wanted to look at. So I might even cut this out and leave that for something that we might need in the problem that we're going to be doing. Now the problem, this is the example that I wanted to look at that sort of points this out and also shows us some things that we're going to come up onto. And this is going to be a pressure vessel. Right, we're going to do more pressure vessel. And by pressure vessel, I don't just mean a scuba tank or some type of pressure vessel that's holding liquid nitrogen or gaseous nitrogen or something like that. I don't mean that. I could mean a pipe. Doesn't a pipe have pressure in it? That's right. And so the pipe is always going to split. A pipe never blows apart long ways, does it? No, it splits along the seam. If I have a pipe, it's always going to split. Let's just say that this is a pipe going through your house. If it ever fails due to pressure, it's always going to split along its length. It's never going to split and the two halves blow up. And you probably, if you've ever seen one, you know, a fracture, a crack in a pipe. Even, and sometimes I'm talking about steam pipes. I had a steam boiler heating system in one of the buildings that I owned once, and it developed small cracks along the length. Luckily, I could fix those. So let's go back to this. So this is the example. The one thing that we want to remember is that my hoop stress is always going to be 2 times my longitudinal stress. And that's what I want to look at in this biaxial stress state. Because if I'm looking at, now I'm going to write triaxial here so that nobody, you know, gets this confused with this. So this really is down here. This is the triaxial stuff. All right. I might even do this. Look at that. I'm going to sort of separate that out of there. Although this is supposed to be down here. Oh no. Oh well. Oh well. So here's the problem that we're going to be looking at. Just like we were in the last problem, we're going to be looking at a piece of skin of this scuba tank. Right? I'm going to make it look thicker than it really actually is, but the actual thickness of the scuba tank, right, is going to be, what did I have? Oh, 6 millimeters. That's right. So it's 6 millimeters, and then I'm just going to look at something that's like 10 centimeters on each side. It doesn't really matter because we're just really looking at the strain in that direction. But you know, I'll give it some distance so that you can see how much larger it would be. All right. That's not what we're really here to see, though, is that if I draw this, what I want to do is I want to draw the hoop stress. Now, the hoop stress is in the y direction. And why do I say that? Because when you look at the pressure vessel, right, the hoop stress is what's coming around in this direction. It should be that going in that direction, actually, because it's ripping it apart, right? It's ripping it apart so that it has like a rip along there. So that's the hoop stress. And then the longitudinal stress is going this way. And that's always much smaller than the hoop stress. That's why the hoop stress always rips that big seam in the side of the pipe rather than the hoop stress ripping the pipe apart and blowing it up. No, if a pipe blows up, someone's put a stick of dynamite in that pipe. Yes. So then this is going to be my longitudinal stress. And so what I want to do in this lecture is I want to analyze what would be the actual extensions and the strains. What would be the strains and the extensions in all 3 of the directions, right? So I'm going to find out what is the strain in the x direction, what is the strain in the z direction, what is the strain in the y direction. And then I also want to find out what the deformation is in the x, z, and y directions too, right? And of course, this will be my x, so sigma sub L, and then my y is going to be sigma sub H. And then the z direction really has no force applied to it. It's just sitting there, so we don't have to really look at, we look at the strain in that direction, but of course, it's only going to be a biaxial stress state. So this is biaxial down here, a problem. All right, so let's just put our strains together then. Well, let's look at the strain in the x direction or the longitudinal direction first. And that's just going to be the stress in the longitudinal direction over E. Oh, you know, I forgot to tell you too, how do we find stress in that? And I can't really derive it yet because that would let the cat out of the bag. But I have actually figured out what the longitudinal and the hoop stress are going to be for this problem. And the longitudinal stress is going to be 166.67 megapascals, and the hoop stress is going to be 333 megapascals. All right. Now you're probably saying, "Wow, that's pretty high. That's close to the 400." Well, I'll tell you what you make a scuba tank out of is pretty darn good steel alloy. Right. So we don't really have to worry about it. A scuba tank could take this, and I'm giving you the non-safety factor. I mean, I say 6 millimeters, but really it's a centimeter, isn't it? Because it's like a safety factor 1.8 on a scuba tank. You don't want that scuba tank blowing up. And if a scuba tank ever does blow up, it's usually where the valve has been knocked off it or something like that. It's fallen over. It's knocked a valve off, and then it becomes a giant air-based torpedo, if you've ever seen one. So let's go back to this. So this is what I've set up, and I wanted to, we'll use this in the equation later on. But what we want to do now is solve it symbolically first. So it's going to be longitudinal stress divided by E, right? Minus the hoop stress divided by E times Poisson's ratio, right? I hope I haven't lost anybody there. And I can simplify this a little bit because I can take that 1 out of E out of there, can't I? And then I could say, well, hey, really, I've got sigma sub L here. So why don't I replace sigma sub H with 2 times sigma sub L? Isn't that the relationship that we've got here? So minus 2 times Poisson's ratio times sigma sub L over E. Oh, wait, no, I've already taken E out of there. Sorry about that. All right. And now I can see that I can take both sigma sub L and E out of the equation. And what I'm left with is 1 minus 2 times nu, right? And we know that for, the steel that we've got here, the Poisson's ratio is 0.3. So this is going to be 1 minus 2 times 0.3. 2 times 0.3 is 0.6. So 1 minus 0.6 gives me 0.4 times sigma sub L over E. Right, see how I got that? Now, let's look at the other one too. Let's look at the hoop. And since we want to be comparing apples to apples, we're going to use the longitudinal stress in here too in the exchange that we've got. But what we get is we get the hoop stress over E minus the longitudinal stress over E times Poisson's ratio, right? So we can take 1 over E out of that. And then if I substitute in sigma for sigma sub H, now we know sigma sub H equals 2 sigma sub L. So I've got 2 times sigma sub L minus Poisson's ratio times sigma sub L. Right, so now I can take sigma sub L out of there. Sorry I wrote that so high up in the first part. So I've got sigma sub L over E. See how I'm comparing apples to apples? Times 2 minus Poisson's ratio. Well, 2 minus 0.3 is 1.7 times sigma sub L over E. Wow. That's pretty big, isn't it? But that is strain in the hoop direction. And we would think that strain in the hoop direction would be about twice what would be in the longitudinal direction, right? So anyway, let's get back to in the z direction, because there is no stress in the z direction, but there is strain. Both of these two things are pulling it in, aren't they? Minus Poisson's ratio times sigma sub h over E, and of course I can put that all over E, minus Poisson's ratio times sigma sub L over E. Now, if I make the substitution that sigma sub h is really 2 sigma sub L, right? What does that allows me to take out minus Poisson's ratio. Well, no, I don't want to take that out of there. Just here, let me do that again. I could take sigma sub, well, let's just do it. Minus 2 sigma sub L over E times Poisson's ratio minus Poisson's ratio times sigma sub L over E. Okay? So, as you can see, we can take Poisson's ratio, sigma sub L, and E out of there. So I'll take the minus sign out too. And then Poisson's ratio times sigma sub L over E, right? And then what is left? That would be 2 Poisson's, or minus, well, no, I got the minus there, plus Poisson's ratio. We got that right? I took the minus out. Minus is extended all the way through, took that out, so I'm left with 2 times mu, or I took mu out. 2 plus 1. Scott, what? It is late. It is later, because I already take the mu out of there, so that's that certainly isn't good. Sorry about that. I'll just take those right out of there. I'll leave the 2 in there because I already taken the mu out. 2, yep, plus 1. So 3. So I've got minus 3 times Poisson's ratio times the longitudinal stress over E. So there you go. We've got all 3 of them. If I wanted to actually write in what those are, since we know it's 0.3 minus 0.3, this is going to give me minus 0.9. Right? Everybody can see that? Minus 0.9 for E sub Z. And then over here, I've still got my 1.7 and positive 0.4. All right? So now if we actually put numbers on this, like let's say, for instance, that the length, the original length, I'll write them over here. My original length of my scuba tank is going to be 1 meter, right? The circumference, because, you know, that's what it is, the hoop all the way around. The circumference of this, which would just be the circumference around there, right? Going all the way around the scuba tank. If I was to look at the scuba tank from the end, that would be the circumference. Well, let's say that the, what would you say the diameter of a scuba tank is? About 8 inches? 8, 9 inches. 4 would be 10, that'd be like 20 centimeters. That'd be like 10 inches. No, not quite 10 inches, that'd be about 8 inches. So 20 centimeters, so let's say the radius is 10 centimeters. So the radius equals 0.1 meter, or 10 centimeters for that. So I'll say that the circumference then, that's 0.1 meters, is 2 times 0.1 times pi 0.6283. 0.6283. 3, wait, that doesn't seem right. 0.1 meters. No. 2 pi 6 point. Yeah, that's right. No, that's right. 0.62 meters. So we want the circumference, and then we want the thickness. So let's say that the thickness, the original thickness, I'll put all of these as sub-zeros. The original thickness was 6 millimeters. So we're going to be subtracting that off of there too. Now, we know what sigma sub L is, so we can figure out, if we know what all of those are, and we know what all the original lengths are, that's the thickness, by the way, or the length. I'll call it the length in the z direction, if you want to think about it. And you could think of this as the length in the y direction. Okay. So the original length in that direction, the original length in the y direction, the original length in the x direction. Yeah. So if I wanted to find out what my new length in the x direction is going to be, it's going to be my 1 meter plus, let's look at it as 0.4 times 166 megapascals divided by 200 gigapascals is going to be 1 point. I think I can definitely say there's going to be a point there. All right. 0.4 times 166 megapascals divided by 200 gigapascals is 332 microns, or 0.00332 meters. So you can see that the scuba tank's not getting a lot longer. And then how about the new circumference? Well, that's going to be the 0.6283 meters plus 1.7 times the same thing. I'm not going to write it out again. Sigma sub L over E, and let me just give that to you because it's 1.7 now. I know I'm taking some time here, but oh yeah, that's not going to add too much to it. So altogether, I get 0.6297. So you can see that there is a little bit of addition there. In fact, it would be 0.0014, right? So this right here is 0.0014, so 0.6297 meters. The circumference has expanded. The length of the scuba tank has gotten just a dash bigger. You know, you can't even notice it. You can't even see it. And how about the thickness, right? The new thickness, because I'm going to be subtracting from that, subtracting the things from that, and I end up getting minus 0.9. So let's do that. So 0.9 times 166 megapascals divided by 200 gigapascals is minus 0.000747. Right, that's the strain. Now I've got to multiply this times point. What did I say? 6? Yeah, 0.006. So that comes to literally nothing. But I'm still going to put it up there. It comes to 4.48 microns times 10 to the minus 6 plus the 0.006 meters that it originally was. So that was 4 times 10 to the 6. This is 6,000. So that would be 0.006. 0, that's 6,000, 0 hundreds, tens, 448 meters. So you can see that it's very small. All of the things are very small. It's not a big enough change that you're really going to see with that type of loading. But that type of loading is a standard loading on a scuba tank. Amazing, you know, the steel is just so amazing that, you know, it just doesn't really change all that much. Aluminum alloy is much the same too. Just wanted to point that out. Now, what I want to do is I've got a little slice of room left here. And so we did triaxial, and then we did a biaxial stress pressure vessel, getting you ready for the pressure vessels anyway, which you pretty much know now, except I just have to derive the thing for the pressure vessel. But what I wanted to look at was shear, right? Oh, wait a second. I think we've already got shear out of the way, haven't we? I'm not sure if we have actually gotten shear out of the way and discussed shear. Shear is where I have like a shear pin or something. I'm just going to look at a piece of material. Instead of having the forces pulling on it uniaxially, we would have a force that's going up this way, and we would have a force that's going down this way, right? And what would that tend to do to the piece that we've got here? This, by the way, is shear. Yes, I should have mentioned this, but we're going to talk about this and get this out of the way. I should have mentioned this before. Biaxial. Well, no, yeah, I don't know. Biaxial is an extension of normal stress and uniaxial stress, so I think those are good. Let's get into shear, though. So shear now is going to tend to shear this thing. So I'm going to exaggerate what's happening, but this now, right, is going to be sheared like this. And you can see that this is going to be pushing down here, isn't it? And this is still going to be pushing up here. So I'm shearing that piece. I want to look at a couple things on there, though, so that we can look at some things. This angle right here, right, I'm going to call gamma. Does everybody see that? It's gamma. And then I want to look at two other, well, actually just, no, two other things. This right here, because we're moving this full distance, right? So this distance that we've actually shifted down is called delta sub s. And this distance right here is L. Let's just call it L for now. I don't want to call it L sub 0 because that'll get you mixed up with the other one. But in shear, we're now shearing this. We're moving this down. This is going up, and we're shearing it. So we're not pulling it apart. We're actually just shearing it. That's why it's called shear stress. Now, if you look at that angle, right, you can see that this angle right here, because this distance is L, that the tangent of that angle, opposite, right, opposite over adjacent. So I've got delta sub s over, wait, is that, tangent. Have I got that right? Tangent, opposite, yeah. Oh, wait a second. Yeah. Oh no, that's the same. That's the same thing. So opposite. Yeah, I'm really looking at this angle, but it's the exact same angle, so it doesn't really matter. So let's see. That would be opposite. Yeah, opposite over adjacent, which would be L. So delta sub S over L. However, we know that for small angles, tangent of gamma equals sine of gamma equals gamma. That's a good rule of thumb to keep, always. In fact, I've never used the highlighter before, so let's give that a try. Look at that. I ran across a highlighter, so I thought I'd use it. Tangent of theta, or gamma, equals the sine of gamma equals gamma. Now, I'm talking in radians. Remember that. Radians. Because engineers can't use it. There are no, radians are the only engineering unit for angles. Remember that, right? We're not using any trigonometric thing when we're talking about gamma. That's really just the arc length that we're talking about there. So for small angles, I mean less than 5 degrees and really less than 3 degrees if we want to talk about angles in degrees. All right, so what we're going to do in the next lecture is we're going to look at shear, and we're also going to clear up thermal. We're going to look at thermal stresses as well and do an example in thermal stresses, and then get into you know, really torsion, starting to get into torsion. Okay. Let me just check. Oh yeah, well, I've been keeping you guys a little bit longer for the last several lectures anyway, so I'm going to make this a short lecture. I don't have any more room anyway, and then I'm going to get into, like I said, just finishing up shearing deformation, the shear modulus, and then getting into thermal stresses too. All right, see you there.